and share the PowerPoint, and we will get going. So I hope everyone's been reviewing their amino acids since Wednesday. Reminder, next week, Friday, it's going to be our first test. And it'll be all online and all that. I will tell you more about it in probably like on Monday. We'll go over that a little bit, but just so you know that's upcoming. Next week, Friday, is our test. And you don't have to take it at 2. You'll have the whole day to take it. I'll open it at 12 a.m. on Friday morning, and it will close at 12 p.m. Friday night. And you have 1 hour to do it. Whenever you want to do it, that's up to you. But like I said, I will explain that more when we get there. Just as a reminder, we looked at our 20 amino acids, and we looked at how we combine those to make a peptide bond. Then we did a little practice about drawing peptides. Like I said on Wednesday, the best way to learn these is just by drawing them. Because the test is online, I don't see a good way to ask you to draw them for me. So I'll probably just show you an amino acid and you tell me what it is, something like that. But the best way to learn them is to actually draw them. You'll have them seared in your mind. And then we talked about pKa's a little bit. How amino acids have ionizable groups, and depending on the pH, the charge will be different. And we talked about this idea of PI, isoelectric point, where PI is simply the pH at which an amino acid or protein or anything is electrically neutral. It has no charge. For amino acids, it's a simple calculation. It's given there on the slide. For proteins, it's harder to do. You can do a rough calculation using computer programs, but mostly it's just done through experiment. What we are going to do, though, is we are going to determine the overall charge for a peptide at different pHs. And for this, I'm only going to ask you to know how to calculate this for 3 different pHs. A pH of 7, a pH of 1, and a pH of 14. So what I'm going to do is I'm going to walk you through how to solve this type of problem for the peptide team. Then I'm going to see how we all do while trying to do ARCHI and these other ones. But let's just stick with team first. All right, let me get my pen out. That. So the first thing you want to do, the first thing I do, is I rewrite the peptide out with the N terminus and C terminus. Remember, the N terminus is always at the first amino acid. The C terminus is always at the last amino acid. So we have NH3, then just T, E, A, M, C terminus, okay? So that's our amino acid for team. Under that, I write the pKa's. So pKa. So the pKa for all NH3 groups, I know on the chart I posted on our Blackboard, each amino acid has a different pKa for the amino group. I'm not going to ask you to memorize all those. We're just going to say it is roughly 9. We're going to say no matter what N terminus it is, has a pKa of 9. Okay. T. Now, when we go to the amino acids themselves, the only thing I care about are the side chains, right? That's the only thing that could be ionizable for our amino acids. T is threonine. If you look at the chart, threonine does not have a side chain pKa. So I'm going to write an X there. It is not going to figure into our calculations. E is glutamic acid, 4.25. And while I'm doing this, I was just reminded, I got a question over email. The pKa's I put on the chart or upload to the Blackboard are slightly different than the ones in your book. Which one should you know? And my answer to that would be it doesn't matter what set you know, because different experiments will give you different numbers, but they're all going to be relatively the same. So in the book, I think glutamic acid's like 4.08. If you learn 4.08 versus 4.25, no question I can ask you, will you ever get it wrong? So you're close enough if you know 4.08 or 4.25. If you said 4.75 or 5, that's wrong. That's way above any number I gave you. But if you know somewhere between 4.08 and 4.25, that's fine. Okay, next one, alanine. Alanine does not have a side chain pKa. Methionine and methionine does not have a side chain pKa. Then C-terminus. We're going to say all C-terminuses are 2. Again, like the N-terminus. They're all different. We're just going to say they're 2. So the first thing I always do is I solve for a pH of 7, because this is the easiest. So for a pH of 7, the way we learn amino acids, their charges, is at 7. On the sheet where it says, negatively charged amino acids, positively charged amino acids, that is for a pH of 7. Inside the cell, the pH is 7. Most of our chemistry is done, not all of it, but most is at a pH of 7. So let's just look at the charges we have for team at a pH of 7. The N-terminus is positively charged, so I'm going to write a plus there. T, the side chain is not charged. E, glutamic acid, negatively charged. A, no charge. M, no charge. C-terminus, negatively charged. So at a pH of 7, I just count up the charges. I have 1 plus and 2 minuses. So the overall charge is -1. Simple enough. Okay, let's go to a pH of 1. At a low pH, pH of 1, that means you have protons in solution. You have a lot of protons in solution, right? And what protons want to do when you have a lot of them is attach to your amino acids. But what amino acids are they going to attach to? That is where your pKa comes in. So let's look at the N-terminus. We said the N-terminus is charged at a pH of 7. We say it is already a plus. Its pKa is 9, okay? Now, if you look at the pH of 7, it's already okay, I'm back. Apparently my internet just crashed. What was I talking about when I crashed? Did I get onto pK of 9, pH of 7 on the N-terminus? And I'm gonna go and write back the joys of internet teaching. Let me go back, N-terminus, T, E, A, M, C-terminus, pKa's 9, X, 4.25, X, X, 2. pH of 7, plus 0, negative, 0, 0, negative. pH of 7 is -1. Okay, so then we go to a pH of, where did I get, so that's the peptide we're doing, right? So we're doing the peptide team. So I just wrote it with an N-terminus and a C-terminus because all peptides start with NH3 and end with COO-. So I just wrote out team. That's what we're working on. And I just wrote TEAM for our amino acids. So pH of 1, like I was saying, lots of protons. We want to protonate our amino acids, but we have to figure out which ones we want to protonate, and that depends on the pKa. So let's start with the N-terminus. So it has a pKa of 9. At a pH of 7, we're already protonated, right? So let's say we go to a pH of 1. Now, at 7, I'm protonated. Going further to 1 won't change anything because I'm already below the pKa. The way I imagine this is that I start at a pH of 7. And if I go down to a pH of 1 and I never cross the pKa, that is, I'm already below the pKa when I start at 7, nothing will happen. I'm already protonated at a pH of 7. Going to a pH of 1 will not protonate me again. I can only be protonated once unless I go to like a pH of minus 20. So I have already been protonated at 7. I can't be protonated again. So we do not change the N-terminus. T does not have a pKa, so I don't care about it. T will never change. E, okay? So E at a pH of 7 is negatively charged. It has a pKa of 4.25. We're going down to a pH of 1. So if we start at 7, it's negatively charged. We're going to a pH of 1. From that transition from 7 to 1, I went below the pKa. I went below 4.25. When you go below the pKa for the first time, that means you become protonated. I gain a proton. Yay, gain proton. A proton is positively charged. So if I was negatively charged at a pH of 7, if I gain a proton, I become neutral because -1 + 1 = 0. So NH3 is positive, T is neutral, E at a pH of 1 is also neutral. A doesn't have a pKa. I don't care about it. M doesn't have a pKa. It's never going to change. C-terminus, same idea. At a pH of 7, I'm negatively charged. My pKa is 2. I'm going to a pH of 1. So if I go below the pKa for the first time, doing this transition from 7 to 1, if I go below the pKa, I gain a proton. Yay. When I gain a proton, I gain a +1 charge because that's what a proton is. If I start -1 and I gain a +1, I become neutral. So my pH my charge at a pH of 1 is +1 and then a bunch of zeros. So my charge at a pH of 1 is +1. Basically, at a pH of 1, anything that's negative in a protein will become neutral. Anything that's positively charged won't change. Anything that's neutral won't change. So that's 1, and that's also a pH of 7. Let's do a pH of 14. Okay, so pH of 14. Let's start with the N-terminus. At a pH of 7, I'm positively charged. My pKa is 9. And if I'm going to a pH of 14, I go above my pKa for the first time. Going from 7 to 14, I go above 9 while doing that. And that's why I always write these numbers out in order from big to small. From 7 to 14, I went above 9. When you go above the pKa for the first time, you lose a proton. You lose a positive charge. So at a pH of 14, my N-terminus does not have a charge. T, I don't care about, does not have a pKa. E, okay, E. So this is E. pKa of E is 4.25. pH is 7. I'm going to a pH of 14. Okay, at a pH of 7, I'm negatively charged, and I'm already above the pKa. If I go up to a pH of 14 from a pH of 7, I'm already above the pKa, nothing changes. Something only changes if I'm switching to a pH that crosses the pKa for the first time. Either I go above it the first time or below it the first time. And always start from a pH of 7. That's like our home base. That's where we feel comfortable at. We want to be at a pH of 7. So E at a pH of 14 stays negative. A we don't care about, M we don't care about, COO, same idea as E, stays negative. And overall, at a pH of 14, our charge is -2. At pHs of 14, anything that's positive will go neutral. Anything that's negative will stay negative. And it's possible for cysteine and tyrosine, they will go from neutral to negative. But you'll never have like double negative on amino acid or anything like that. Yeah, so when you go from, when you go to high pHs, your proteins lose protons. When you go to low pHs, you gain protons. The pKa will tell you which residues will gain protons, which one they will lose protons. All right. I know that was probably confusing because it usually is. What I want you to try to do, though, is see if you can follow my madman scribbles that are on the PowerPoint and tell me what the charge of Arche is at a pH of 1, a pH of 7, and a pH of 14. If you get to the point where you have an answer, feel free to send me a private message about that, or if you want to tell everybody what your answer is, you can tell everybody if you want. If you have questions, I might be able to help. But the best way to do this is just to try and then see what point you're stuck at. And if you have a specific question at that point, that would be, I can help a lot better than at that point if you have like a specific question you can ask about this. But yeah, give that a whirl and see if you can figure out what the charge of Arche is at 1, 7, and 14. So what you want to do as your first step is write down the pKa for every amino acid in the N-terminus and C-terminus. And what is charge at a pH of 7? First just figure out, based on my amino acids, what is positively charged, what is negatively charged at a pH of 7. Once you have 7 figured out, and 7 should be the easiest. Once you learn your amino acids, you learn what the charges are at 7. Just as a reminder, your positively charged amino acids are K, R, and H. Your negative amino acids are D and E. Everything else is neutral. Once you have that figured out, once you have all the pKa's written down, just ask yourself, going from a pH of 7 to 1, if I go from a pH of 7 to 1, is my pKa between 7 and 1? If it is, I lose a proton. If it's not, nothing changes. Or sorry, not lose, gain. You gain a proton. When going from a pH of 7 to 14, if my pKa is in the middle of 7 to 14, I lose a proton. If my pKa is not between those two numbers, nothing happens. How do we know if a neutral amino acid becomes negative and losing a hydrogen or just neutral? A hydrogen is a +1 charge, so if you ever lose a hydrogen, you go down a charge. So if you're neutral, and you lose a hydrogen, you become -1. Yes, remember, a hydrogen's +1 charge. If you lose a +1, you become negative. And again, if you have any answers for Archie, let me know so I can see how people are getting on. Feel free to just send me like a private message. Let me clear some of my madman writing and slowly do Archie. Maybe another example will help people with this idea. First thing first, write down your amino acids with the N and C terminus. NH3, A, R, E, K, Y, C, O, O. Write down the pKa's. pK of every N terminus is 9. A does not have a pKa. arginine has a pKa of roughly 12.5. Glutamic acid has 4.25. Lysine, K, special K, 10.8. Tyrosine has a pKa of 10. C-terminus, 2. So unlike our previous example, Arche has a lot of ionizable groups we have to worry about. pH of 7. Again, eventually this will become secondhand nature to you because we learn how to recognize amino acids at 7. Your positive ones are R, K, H. Your negative amino acids are D and E. So N-terminus, positive. A, not one of our 5, no charge. R, positive. E, negative. K, positive. Y, not one of our 5, neutral. And C-terminus, COO minus. Count up our charges. 3 positives, 2 negatives. Overall, that'll make 1 positive, right? So +1, +1, -1, +1, -1. Overall, the charge is +1. And what you'll notice when you start to do this too, is at a pH of 7, you can ignore the termini because they always cancel each other out. You always have a positive termini and a negative termini. So all you care about are the amino acids. Why is Y neutral? Because it is. So that's because it has has a pKa of 10.07, right? And it has an OH group. To get rid of the proton of tyrosine, you have to go above a pH of 10. At a pH of 7, we're below that, so it's neutral. Yep, there are only 5 charged amino acids at a pH of 7. RKH, DE. I would get that seared into your mind. Positive RKH, negative DE. What do I get a pKa of 9 from? That's all N-termini. That's my statement. All alpha amino acids for this class are going to have a pKa of 9. All alpha carboxy are going to have a pKa of 2. Otherwise, you would have to learn 40 values, which is pointless. So we're just going to say they're all 9 or 2s. Now I'm getting that from the pKa sheet I put online. pH of 1. Going down pH is relatively easy. Anything that's negative will become neutral. Anything that's charged will stay the same. Positive stays the same. A doesn't change because it's neutral to begin with. R is positive. E, it's negative and it becomes neutral. K, positive. Y, neutral, so it stays neutral. C terminus, negative, so it goes neutral. So at low pHs, well, specifically at a pH of 1, this rule only works at a pH of 1. If you go to a pH of 1, anything that's negative will become neutral. If you go something like at a pH of 3, that's when that won't hold. But at a pH of 1, it does hold. And I'm only going to ask you a pH of 1 for simplifying matters. All right, so pH of 1, what are our charges? Positive, positive, positive. Everything is neutral, +3. Okay. pH of 14. We start. And when you go to a pH of 14, ignore everything you did at a pH of 1. It's easier to just start from home, from base camp, a pH of 7, and go from there. So first off, anything that was positive at a pH of 7 will become neutral at a pH of 14. So N-terminus, neutral. A, neutral. R, neutral. E, anything that's negative will stay negative at high pHs. So E's negative. K is positive at 7, so it becomes neutral at 14. Y is the interesting case. So Y, at a pH of 7, Y is neutral. Y doesn't have a charge. Its pKa is 10. So if we go to a pH of 14, 10 is between 7 and 14. Since our pKa is between 7 and 14, we will lose a proton. So what will happen is that Y will go from neutral and it will go to negative. So Y is negative. COO, negative. If it's negative at a pH of 7, going to a pH of 14 won't change that. Negative. So if we look at our charges now, neutral, 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 -1, neutral, -1, -1. Overall, our charge is -3. And that's archy. At least I think that's how you pronounce that word. So now that we've seen 2 of them, questions about that? All right, so by my count, that's been roughly a half an hour on how to figure out these problems. So I'm gonna leave B, C, and D for you to do more practice on, and the answers will be uploaded so you can check your work to see are you getting this idea. Is it supposed to be -2? Nope, it's -3. Because the Y is negative, the E is negative, and the COO minus is negative. There's no positive charges to balance that out. Okay, so let's clear this. Bye-bye math. Not really math, just counting. The last thing we have to get on this slide, on this slideshow, is simply the ideas of enantiomers and Fischer projections. So we just start with the question, what is a chiral molecule? And for us, a chiral molecule cannot rotate on its mirror image. So if pK is between the pHs, it loses a proton. If the pK is not between the pHs, nothing happens. Yep. Well, it can also gain a proton. So if you go from 7 to 1, and the pK is between 7 and 1, it gains a proton. If you go from 7 to 14 and it's between that, it loses a proton. So it depends which way you're going. Anyways, a chiral molecule is something that cannot rotate on its mirror image. So on here we have an example of that. Here's our molecule. If we rotate this molecule on the left, we get CH. This Cl is going away from us. This F is now coming at us. This Br is going away from us. Just good old organic chemistry. Remember, the wedges mean they're coming at you. The dots mean they're going away from you. Straight lines are in the actual plane of the screen. So a chiral molecule, the definition is can't rotate on its mirror image. A simpler definition for us is a carbon that is bound to 4 different molecules or 4 different groups. If you have a carbon with 4 different groups, that's a chiral center. That's mainly what we look for. And we have this idea of enantiomer. Enantiomer are pairs of molecules that are mirror images of each other. So these 2 molecules up here are enantiomers. They are just mirror image of each other. They have the same atoms bonded to carbon, just different geometry. And what types of amino acids, L or D, are normally found? So does anyone actually know that off the top of their head? On Earth, 99.9% of all amino acids are a certain chirality. And in biochemistry, we say R, L, or D. And organic, you use like R and S. They actually don't mean the same thing. So I'm not going to get into what L and D actually means. Just think of them as similar to R and S. But does anyone know on Earth, do we have L amino acids or D amino acids? And the second part of the question is, why don't we have both types of amino acids? Yep, we have L amino acids. Why would we not have D amino acids? Why not be 50% L and 50% D? Does anyone have any thoughts onto that? Evolution or summon? Kind of, I guess. Why is it beneficial? Isn't it because it could be dangerous? It's dangerous to us now. I'm just saying, like at the very beginning, why not have both? Probably just happened. Yeah, I guess that was my next question. Why L instead of D? And the answer is, I don't know. Just picked one. Whatever organism had L amino acids won out over anything that had a D. And we're all from that one organism eventually. So we all have L amino acids. But why not have D? I mean, there has to be some reason, right? Left is better. There's basically no difference between L or D, other than the one chiral center. Like no differences in free energy, like no differences in like melting point, no chemical differences except that one carbon. They behave differently. No, they more or less behave the same. You could not tell L-glycine from D-glycine. Well, glycine's horrible. L-alanine or D-alanine unless you had like an instrument that tells you. So let me answer that for everybody. Thank you for sharing your ideas. That's part of the learning process. Get our ideas out there. And never be afraid to be wrong, because if, like I said, if you are never wrong, why are you in my class? Maybe cells are just using the L stuff. They don't know how to do D anymore. Kind of along those lines. So enzymes. Enzymes are proteins that do biochemical reactions. They are so specific that if the, I can't spell. They are so specific in their reaction that if you tried to give them a D amino acid, they would fail. they would not be able to work on a D amino acid. So if you had L amino acids and D amino acids, what that would mean is that you'd have to have 2 copies of every single enzyme in your body. One that works on L amino acids, one that works on D amino acids. And it would just be a mess when you're making like new proteins. You'd have to have like different ribosomes or different like tRNAs to try and distinguish between the two somehow. The machinery would get so much more complex just from a little change. So to simplify things, it is way more energetically efficient if all of your enzymes just work on one type of amino acid instead of just making enzymes to work on another type. So that's why pretty much all life on Earth has one amino acid. Now, if we go to another universe that uses amino acids, they could have D, and they could be all D amino acids. There's no reason why it couldn't happen. It just didn't here. The wobble effect is when tRNA is binding DNA. Enzymes don't really have that much of a wobble effect. There are side reactions for enzymes. But if you try to give an enzyme a D amino acid, it'll just get stuck and not be able to work. Enzymes pockets are incredibly specific, as we'll see. So that's basically the reason. We do find D amino acids on Earth. They're in what are called the peptidoglycan layer. Peptido means proteins, glycan means sugar. Peptidoglycans are the outside layer of bacteria. So if I'm a little bacteria, my outermost layer is sugar protein, and inside I have D-alanines. I have D amino acids. What benefit is there to having D amino acids on the outside of my cell? Why would that be beneficial to a bacteria? Why would a bacteria go through all the trouble of making a D amino acid to put on the outside of its cell? They're harder to destroy because everything else is L. Yeah, exactly. So if all the proteins in the world, all the enzymes in the world work on L amino acids, wouldn't it be genius if on your outside protection layer, you put a D amino acid to say, ha, I am now invincible. You cannot work on me. So on the outside of bacteria, they have D amino acids. However, we, organisms, have evolved to create proteins that will chop apart their D amino acids. So like inside your tears, you have a protein called lysozyme. Lysozyme can chop up the peptidoglycan layer. Other proteins can do that too. So they created a defense, and like evolution, they created a defense. We create something to destroy their defense. So that's why they probably have it, but there are ways to destroy it. We will re-evolve to only have D. I don't think that'll happen. That'll take so much energy, and maybe in like 5 billion years, possibly. But well, they don't only have D. They have one D amino acid. Everything else is L. They just have one D amino acid on their outside, just D-alanine. Everything else is L. So, and if you chop that apart, the bacteria dies. I always say peptidoglycan layer. Peptidoglycan. So I put my emphasis on like the dough, and then because glycan's a word, right? Peptido is a word, so peptidoglycan. So I guess it is possible that all bacteria will have D at some point. I just find that unlikely because once you kill the peptidoglycan layer, you kill the bacteria. So if you get past that layer, like having D elsewhere aren't going to do anything, because basically cutting the peptidoglycan layer just kind of makes the bacteria spill its guts out a little bit. So it's death at that point. All right, so that's some fun thoughts experiments with L and D amino acids. The last thing I simply have for you, and then we'll call it a Friday, is here's a bunch of molecules. Here's our journey back to organic chemistry. Can you tell me if these molecules are chiral or not? And I'll put up a poll to see where we're at on this. Since this is just a straight up yes or no, tell me, are the molecules we're looking at chiral or achiral? And while you work on that, since we just finished Wednesday's slide, what I'm gonna do is the material we were supposed to cover today, I'm gonna move that to Monday. And so the reading guide that's normally due on Monday, it won't be due on Monday. If you already did it, great, you have it done. But I'm gonna push everything back like one day. So I'm gonna rename all the folders, manually reset all the due dates, but our test will still be on Friday. I'm not gonna move the test back because the amount of material we cover won't change. Because basically what we cover on Friday, I believe, should be the last thing we cover for the test, or what we cover on Monday. So basically, if you haven't done a reading guide yet for Monday, you don't have to do that till Wednesday. If you already did, you're good for the week. But I'll make that change probably later today, because that's actually quite a bit of work to go in there and change all the due dates by hand. Fun times. So remember, chiral is rotate on it, cannot rotate on its mirror image. Achiral means it can. Or for us, it means, can you find a carbon with 4 different things attached to it? What makes a carbon an alpha? Where it is in an amino acid. Let me draw that. If it's between the N and the C double bond O, that's an alpha carbon. That's how we name carbons for amino acids. The next carbon up would be the beta. Then I believe it goes delta. I'm not too up on my Greek, but it just follows the Greek alphabet at that point. But the alpha beta is really the only one we care about in terms of naming. And it's always between the NH3, the N terminus, or the amino group and the carboxy acid group. Next Friday, I will not have a lecture. I will just make the exam live at 12 a.m. Friday. You have 11:59 p.m. to finish it on a Friday. Once you start it, timer goes. So let's say you start it and your internet crashes, the timer's going. So make sure you are in a spot where you will not be bothered for an hour, and a spot where you are confident of the internet connection. I will give more information for that. You will probably have to have a camera on. Because what's probably going to happen is that a computer program will watch your recording. And if there's any suspicious behavior, it will flag the video and tell me why there was why there was that flag. Suspicious behavior, there we go. And then I get to go and look at the video myself and either confirm or deny. So all good stuff. But I'm gonna get that all worked out probably on the weekend and get back to you. Well, no one's actually going to be watching you. A computer is going to analyze your video. And there's also an option on that, which is kind of creepy, but I get to go in and watch you anytime I would. If you're in the test, from what I've heard, I can go in and watch you while taking the test, and it won't tell you I'm there. So be decent on camera, I guess. I don't know. Just imagine I'm going to be watching you. That's all I'm going to do Friday. How many questions will be on the test? I don't know. Have not made it yet. The practice tests I put up online are a good indication of the length of tests. So time yourself to see how long it takes that. That's generally how long I shoot for. The fastest students on my test in biochem can finish in 25 minutes. That's probably the fastest. By the end of 50 minutes, in a class of like 20, there's usually only 3 to 4 people left. So most people have it. You don't have a college ID, but I think all you need is Blackboard. And like I said, I'll have more information once I look into it a little bit more. I don't think you need to show like a college ID. I think you just need to show your face on the camera. But I'll give you more information. All right, let's take a look at this. What time is it? Oh, it's time to go. Sorry, I went babbling on there. Okay. A, chiral. Yes. Like I said, just look for a carbon with 4 different groups. If you want to do like plane asymmetries, that's fine too. Basically, a plane of symmetry, if I remember my organic right, is that you just like draw a line and see if it can fold on itself. And if it can, it's achiral. If it can't, it's chiral. I don't do that. I just look to see, do I have a carbon with 4 different things attached? I do. So here at this carbon, I have a Br attached, a CH3, I have a hydrogen right here, and then I have this group. So there's a carbon with 4 different things. That makes this molecule chiral. So A is chiral. Let me get my sheet to make sure I just don't say something off the top of my head and say it wrong. B is chiral. This carbon has 4 different things attached because remember, there's a hydrogen here. C is chiral. Many carbons, but that carbon has 4 different things attached. D is chiral. Yeah. So this carbon has 4 different things attached. Remember, hydrogen here. So for rings, you just go around the ring. And if you hit different things along the ring, so like on this carbon, I hit this aliphatic group. Here I have a CH3. So technically, when I go around the rings, they're different. So that makes something chiral. So D is also chiral. E, chiral, right? Because my ring is not symmetric. I can't fold my ring like to a sandwich and get the same image back. F, I can though. So F does have like one of those planes of symmetries where I draw a line down the middle and then I fold it over. It's the same thing. Also, there's no carbon with 4 different groups. All right. If you go around to every carbon, there's no unique carbon. There's no carbon with 4 different unique groups onto it. So F is achiral. G, same idea. G is achiral. There is no carbon, no matter where I start from. No carbon has 4 different things attached to it, especially since there are double bonds. Most of those carbons don't even have 4 groups to begin with. So G is achiral. H is chiral. Like this carbon has 4 different things attached to it. So no, that carbon actually doesn't. This one would. Because when you go around the rings, you find a different path. If I had a C double bond O up, it would be right here, wouldn't it? yeah, if I had a C double bond O right there, that could make it achiral, but I don't. So that's chiral. So that's your little refresher into organic chemistry, chiral, achiral. We're not going to worry about that all that much throughout the semester. It's mainly just due to having different chiralities of amino acids. All right. And with that, that ends our lecture for today. So I will post this video online as always. I will post the homework as well. So make sure that you do that. There should be 2 homework assignments that are due Sunday night. I will get all of the logistics for the test figured out, and I'll be sharing those probably on Blackboard by Monday, and then we'll go from there. As always, if you have questions, please let me know. Please reach out. Otherwise, I hope everybody has a fantastic weekend, and I hope everybody is studying your amino acids. All right. Take care.